Hello, everyone. My name is Wojaczynski. I'm a postdoc at Astrocent, which is a part of Nicolaus Copernicus Astronomical Center in Warsaw. And today I'm going to talk about the DarkSide program and the DarkSide collaboration in general, and also general things about the dark matter program. Right. So according to current estimations, the atomic matter consists of only, sorry. Oh. Okay. Yeah, that works. Okay, yeah. Yeah, so according to current estimates, the atomic matter consists of only like 5%. So everything that we see is just 5%. So the rest is hidden in the mysterious dark matter that we know. The models varies from like 25 to 27%. So we don't know exactly what it might be. If it's still baryonic, then it could be like mature objects, black holes, neutron stars, or brown dwarfs. Here, right? But it seems like there's just not enough of these objects to account for this hidden mass. So if in turn there are not baryonic, if the dark matter is not baryonic, then it could be like hot relativistic neutrinos could be a solution, or maybe just completely different shape of matter. It could be like this WIMP particles. So very popular theory right now. That varies the WIMP particle from, it varies the masses between like tens of GeVs up to teraelectronvolts, more or less. So yeah, there are like many evidences that dark matter exists. I put the rotation curve at the first place. So yeah, what we see exactly with the luminous matter is completely different than the rotation curve that we observe. So it seems like far from the nucleus of the galaxy, there is much matter hidden, what makes the curves almost flat. The other is gravitational lensing, for instance. So at objects which like aren't massive enough to bend the light the way it is bent. So yeah, we can look for dark matter in different ways. We can try to detect them in a direct way, like we do for WIMP scattered on nucleus. But of course, we can try to detect it also in non-direct way, like try to produce it in accelerators maybe, or observe some products of decay or annihilation of dark matter. That could be like antimatter, gamma ray photons, or neutrinos. So the DarkSide program focuses on directly searching for the WIMP. All of the detectors that were built share common design, which is a two-phase Argon time projection chamber, so the TPC. The goal is to have really low background, almost background free, and free from interactions like neutrons, betas, gammas. So we started in 2011 with the, oh, sorry, I did it. Control, yes, thanks. So we started in 2011 with the first prototype, the DarkSide 10, which was a 10-kilogram prototype. Then it was followed by the DarkSide 50, 46 kilograms of liquid argon, also operated in Gran Sasso, Italy. But then, of course, the collaboration decided to push into building some bigger detector. Yeah, now the goal focuses on building the DarkSide 20K, which should have around 50 tons of liquid argon, 20 tons fiducial. But in order to do that, of course, a set of new prototypes needs to be built first, and that was the Proto series in the years in between, especially Proto 0 and Proto 1. That was like almost a scaled down version of DarkSide 20K detector with all with all the needed technology to be tested inside. So what's so special about the noble liquid detectors? Well, they are quite dense and easy to purify, and they are offering good scalability from small to large scales, which is advantage over gases and solid targets. They offer high scintillation and ionization, and which is very important, they are transparent to their own scintillation. So in terms of TPC, they allow also for amplification for ionization signal. And they offer very powerful technique, which is called pulse shape discrimination. Like here, right? Which offer discrimination between the electron and nuclei recoils. So here I noted some differences between the liquid xenon and liquid argon detectors. So for the liquid xenon, it's denser and radio poor, and it offers a lower energy threshold. On the argon side, it operates on lower temperature, and then removing, for instance, radon is easier. They offer this stronger electron recoil discrimination via pulse shape technique. But still, they have this intrinsic electronic recoil background that comes from argon-39, and they need a wavelength shifter to properly operate. So the general principle of working detectors like this is that we have the time projection chamber, TPC, and this hypothetical particle collides with nuclei with argon nuclei inside the TPC chamber. Then, due to the excitation and ionization, the first signal, the first pulse of light is produced. It's called S1. Then those electrons that survive recombination are drifted up to the anode here. There is a drift field in the whole TPC chamber, and they are extracted at the border between the liquid phase, which is here, and the gas phase, which is just above. They are extracted at the grid and further amplified with another field. And then they are producing second pulse of light. It's called S2 in the gas pocket. And by the difference of time between the S1 and S2 pulse, we can derive the z coordinate of the particle. While when it comes to x and y position, we can deduce it. We can calculate it from the S2 light pattern on the array of photomultipliers on top and bottom of the TPC. So a couple of words about the pulse shape discrimination technique. So there is like two characteristic bands, WIMP-like band for nuclear recoil band created in F90 parameter space. So F90 is a parameter that just calculates the amount of light, the integral of light in the first 90 nanoseconds of the pulse versus the whole integral of the whole signal. So with this pretty straightforward technique, we can easily distinguish between what happened inside. Was it the electron? Was the electron, or maybe a particle that could be a WIMP? So with this, for instance, in a electron recoil, there is a long tail, which makes the F90 parameter smaller. So the average value of this is more or less 0.3. For the nuclear recoil band, the tail of this pulse is quite flat. That is why the whole overall parameter is like closer to 1. And yeah, the average value for this band is around 0.7. So this is the overview of the detector that was built as a second one in this DarkSide chronology. So it was built in Grand Sasso laboratory. It consists of 50 kilograms of liquid argon. There is like 2 VITOs that surrounds the TPC. So the liquid scintillator VITO, and the water Cherenkov detector that wraps the detector from the outside and tag muons. So we had a couple of analyses. The longest one was for 500 days. That was published in the papers like this. Right now we have a couple of new papers with new with the data from DarkSide 20, with DarkSide 50, with their some possibilities to like lighter dark matter particles. So the whole detector was like viewed from top and bottom by 90 PMTs, and yeah, this plot presents more or less what we get after applying all the cuts. So of course, inside the band 0.7 more or less at this level, we get just 0 events. So this is a plot that shows the typical backgrounds in a detectors like this. So this is based on DarkSide 50. So in a detector like this, we have more or less most backgrounds come from intrinsic argon, argon 39, which has to be further reduced, and also krypton 85 from beta decay. This is the blue plot here. And also on the similar level are the gamma rays that come from elements of the detector, so the PMT and cryostat, for instance. So here. So here are also some spectra for a couple of masses of WIMPs. And as you see, for the lower masses, they are like obscured a bit with the events that we call spurious electron events. They are like delayed electron events. They are related to impurities in argon. They are not completely understood, and we are trying to resolve this and push the analysis into lower regime in order to be able to see the spectra for the lower WIMP masses. So underground argon, intrinsic radioactivity in atmospheric argon is the primary background for argon-based detectors, and the collaboration decided to use the underground argon instead, which has a reduction factor of around 1400. So that's the first step, to use the underground argon. So the argon 39 is just a cosmogenic isotope, and using underground argon can give us like significantly lower levels of this isotope. So actual extraction of the of underground argon takes place in a facility called Cortez in Colorado. So we want to reach the capacity of around 300 kilograms per day of underground argon. The next step of preparing the argon for our purpose is to isotopic purification that takes place in a Cerucci mine in Sardinia in Italy, where in future the big tall column will be built for this purpose. And we expect that factor of 10 will be further like reduction of argon 39. We expect to have it at this level. So right now, all of the argon experiments are focusing into building one detector, and created a global dark matter collaboration in 2017. So more than 500 scientists is working on that from 14 countries, as far as I remember. So there is guys from Deep, DarkSide, MiniClean, SnowLab, and IRDM. The DarkSide 20K should have 200-ton-year fiducial volume, It will be built on the same place that all of the other detectors were built before. But also there is a next detector on the horizon, Argon, which will have like 300 tons of liquid argon. And this in turn will be built in Snowlab, but this is probably a perspective a couple of years from now. So this is a structure of the photosensors that will be used in the DarkSide collaboration. So previously in the DarkSide 50, we have this typical PMTs, photomultipliers, but in order to have like better detection efficiency of around 35%, we switched into the SIMPs, and this is more or less the structure, how it should look at the end of construction. So at the bottom we have the typical TPC optical plane that will be that will view the TPC chamber from top and from bottom. There should be like 264 of those elementary panels, PDU called PDUs, photo detection units, 20 per 20 centimeter. Each of this is further created from another smaller structures, photo detection modules, 5 per 5 centimeters, and then we can go to this simplest single photon avalanche diode. This work is prepared with collaboration with. They were developed with collaboration with Fondazione Bruno Kessler from Italy. So yeah, a couple of words about the detector, the 20K. It will be built at the same place, so in Gran Sasso laboratory. So this is around like 140 kilometers from Rome, more or less, under the Gran Sasso mountain, shielded with 1,400 meters of rock. We expect the detector to work for around 10 years. And yeah, this I said, so 50 tons of argon, and we expect to have very low background, so smaller than 0.1 background even in 200 ton year exposure. That would be the world leading sensitivity. So this is more or less the structure of the detector. So this is in fact like 3 nested detectors. Inside, as a core, the TPC chamber, 50 tons of underground argon, PDUs, goal of course to detect dark matter. We expect this very low backgrounds there. Then it is wrapped by the inner vita, which is a vita for neutrons and gammas, and is filled with 32 tons of underground argon. The goal is to capture neutrons. I'm going to talk about that in a second. And then around, as a outer layer, there is outer vita, which should vita neutrons from cosmogenic muon showers, and it's going to be filled with 650 tons of argon, atmospheric argon. And yeah, so this is more or less the details of the TPC. So yeah, most of the things I already described. So yeah, it has octagonal shape, the cathode anode coated with new transparent conductor, and also the wavelength shifter. So like I said at the beginning, for the argon detector, that needs to be used because argon emits UV light, so 128 nanometers more or less, and then it needs wavelength shifter to convert it to visible light to 420 in order to be captured by the SIMPs modules. So here I noted some other properties. So the drift field in the TPC chamber, 200 volts, that is the standard value also for DarkSide 50. The extraction field that extracts electrons from the liquid phase into gas phase. And we expect the spatial resolution, so X and Y below 5 centimeters and Z coordinate around 1 millimeter. So the principle of working the inner vita is like this. So neutrons are a threat because they can be easily like mistaken with the WIMPs. They have the same signature and they are in the same F90 parameter space. They occupy the same region, so around 0.7 parameter. So that is why some other technique is used. PSD is useless. Full shape discrimination is useless. And that is why, of course, the additional structure, another method needs to be built. So there is a gadolinium-loaded acrylic walls that are covering the TPC, and then there is a layer of underground Argon veto, which is the place where actual veto of neutrons take place. Well, it works like this. So in fact, when we have neutrons coming into the TPC, it is then moderated, captured and moderated by the acrylic, gadolinium-loaded acrylic shield, but the gadolinium. So the gadolinium then emits gamma rays up to 8 mega electron volts. Those gamma rays are interacting with argon nuclei here in this layer, and they are producing UV photons, just like usual happens. Then at the TPP layer, so the wavelength shifting layer here, they are converted into visible light, like here, and then in turn they are detected with the VETO photo detection unit, VETO PDU, which is like placed in many places inside the detector. So that method should give us coincidence signal together with hypothetical particle that would enter the TPC. Right, I am about to finish. Okay, so this is just the current situation. So right now in Hall C in LNGS, the structure is this cryostat structure started to be built. There are ongoing procurement for cryogenics and cryostat, also ongoing works on photoelectronics. So sim production already started with L Foundry company. There is a new facility in Nowa Oficina Sergi near LNGS that is dedicated for testing sims, and also another facilities in different places, Naples, Liverpool, Edinburgh, for testing VETO PDUs. So here I'm showing the sensitivity for the dark side for a couple of scenarios. So fiducial mass, the red one, with 5 and 10 years of operation, together with currently working experiments, Xenon NT and LZ. So that should give really nice limits at the time when DarkSide 20 will be built. But of course, there is another detectors, Argon and XLZ, on the horizon that would another beat the result from the DarkSide 20K probably. So as a final word, there is also a second detector that is going to be built by the DarkSide collaboration. It's called the DarkSide Low Mass. It's very small, 1.5 tons of liquid argon, 1 meter of the size of TPC, 1 meter in each size, more or less. And this one is dedicated only for lower WIMP masses, so below 10 GeV. And it will use only the ionization signal, so S2 signal only to have better sensitivity in lower masses. So here I'm showing some plots for this detector from the paper that already was published. So depending on the level of impurities that we will achieve and the level of analysis that we will apply, so this is the threshold for the ionization events caused by the spurious electron, we hope that we will gonna reach the neutrino fog at some significant level. Then we'll see what happens next. Okay, so the summary, it seems like all the things are in place. The TPC is well prepared, well developed. We have this surrounding projects like Urania and Aria. They are quite well developed for our purpose. We have new SIMS production, the test facility ready. We started building the cryostat in Hall C at LNGS. We hope that it's gonna hit the test sensitivities at the time when the detector will be built. And of course, there is the low mass detector dedicated for low WIMP mass is complementary to other detectors built by the DarkSide. Thank you.